I would like first to thank to the organizer for inviting me to this talk, to this very interesting event. Okay, first, let me present my institution, the University of Almería. It's not, I can, okay. Almería is here in the southeast corner of Spain, and this is our university. It's a campus by the sea, and CSOL is a research center, a joint research center between the University of Almería and the Plataforma Solar de Almería. In CSOL, 6 groups, different research groups are working currently in different items, such as organic metallics and photochemistry, water treatment, environmental chemistry, photosynthesis, desalination, process modeling, automatic control of solar processes, building conform assessment, solar cooling, and solar resources assessment. And we are very proud of our equipment because it's a very well equipped center, especially for those equipment for wastewater analysis, especially liquid chromatography coupled with mass spectroscopy. So we are able to analyze very, very low concentration of contaminants in water or in wastewater. Around 60 researchers work at CSOL with an average annual budget of €1.5 million. This budget is competitive budget. We obtain all our funds in competitive calls. The mean number of projects ongoing simultaneously, it's around 30 per year. And as for scientific production, our mean, on average, production is around 100 scientific paper in international journals. So let's move to the presentation itself. We know that half of the world population will be living in water-stressed area in 2025, so it's very close. And this trend will require better use of wastewater as an important source of irrigation water all over the world. Nonetheless, the conventional wastewater treatment plants are not efficient in pathogenic bacteria inactivation, or that is water disinfection, and in the removal of contaminants of emerging concern. Therefore, there is a need, an urgent need, of new tertiary treatments. In this sense, these advanced oxidation processes have been proposed as new tertiary treatments. There are several chemical systems to work with advanced oxidation processes, but among them, only photo-Fenton and heterogeneous photocatalysis are able to use the solar radiation as irradiation source. I will speak in this talk about the solar photo-Fenton process because it's very interesting since it's much faster than the heterogeneous photocatalysis for the removal of persistent organic contaminants and bacteria inactivation in complex media such as wastewater. This process, I will be very brief with the chemistry. This process relies on the reaction between ion, ferrous ion, and hydrogen peroxide to give ferric ion and hydroxyl radicals. This reaction 1. The next reaction is the photoreduction of ferric ion with the backduction of light, UV light, to give, again, ferrous ion and hydroxyl radicals, reaction 2. If we sum both reactions, we have a cycle where ion is oxidized and reduced, and the H2O2 is consumed, giving hydroxyl radicals. These radicals can react with the organic matter or with bacteria, destroying the contaminants, okay? So we have in the set of reactions, there are many, many reactions, some reactions which are efficient for the treatment, and other ones who are not efficient for the treatment. So we need to balance both kinds of reaction during the treatment. The solar photo-Fenton process is strongly dependent on the pH because the photoactive species, that is the ferric ion, is soluble at acidic pH. The optimum pH is around 2.8. Nonetheless, there is a new trend of research in solar photo-Fenton, and it's working at neutral pH. At neutral pH, we have the problem of ion precipitation, and it is solved by the use of some ion complexing agents, like this one, EDDS. I'm not going to say the name, the scientific name, but with this complex ferric ion 3 EDDS, we can work at neutral pH. So, in the next step, what are the main factors to consider when designing a solar photo-Fenton reactor? This is interesting to take in mind. As inputs, we have, of course, the solar radiation availability, the operating pH, if we're going to work at acidic or neutral pH, the catalyst concentration, that is ion concentration, or the oxidant concentration, the H2O2 concentration. And that is very important, I will speak it later about this, the kind of wastewater we're going to use. As output, we need to calculate the solar collector surface area, that is the main dimension of the reactor, the reaction times or reaction rate, the reactant consumption, and taking into account all these factors, the cost of the treatment, because someone has to pay. Okay, so it's very important, the cost. The main product will be at the contaminated water. As for the reactors, the most popular reactors are tubular reactors equipped with compound parabolic collectors for solar light collection, okay, known as CPC. Here we have a picture of an industrial plant, a 150 square meter CPC plant installed in Almeria to treat toxic wastewater. In the last 5 years, our group proposed a new option, is the use of low-cost reactors, such as raceway pond reactors. They are very cost and are open reactors. They consist of, here you can see one, channels where the liquid, the water, is set in motion by a paddle wheel. And we can develop the photo-Fenton process with a very low cost. Let's pay attention now on the impact of pollutant concentration on the performance of the photo-Fenton process. That's why I said that it's very important to take into account the kind of wastewater we want to treat. When we treat highly polluted effluents, such as toxic wastewater, industrial wastewater, the contaminant concentration is in the range of milligram per liter to gram per liter. Normally, the main aim of the treatment is the reduction of the organic carbon content, that is, say, mineralization, along with a biodegradability enhancement, in order to make this water treatable by a bioprocess. To this end, we need a great amount of hydroxyl radicals, HO, okay? And To produce these radicals, we need high concentration of catalyst, ion, and high concentration of oxidant, hydrogen peroxide, okay, in the range of 1,000 of milligrams per liter of hydrogen peroxide. Normally, when we treat industrial wastewater, the volume are small, so we can work at acidic pH. And the reaction rate, the reaction lasts 4 hours. So we measure the treatment times in hours. This is very important too. When we treat effluent containing microcontaminants, the picture is totally different, such as treated urban wastewater or treated agri-food industrial wastewater. In this case, the contaminant concentration is in the range of nanograms or micrograms per liter. So 1,000 times lower the concentration, okay? Among microcontaminants, in the last year, we are paying a lot of attention to the contaminants of emerging concern. That is mainly pharmaceutical, personal care products, some pesticides. In this case, the main aim of the treatment is the removal of this kind of contaminants, of micropollutants. Only the removal of these micropollutants, along with a removal of chronic toxicity, because this kind of substances produces chronic toxicity in the water. As the concentration is very low, we know a low amount of radicals. And to get this low amount of radicals, we use low amount of catalyst and low amounts of hydrogen peroxide, typically around 30 or 50 milligrams per liter, so much lower than the former case. If we want to treat urban wastewater, the volumes are very large. So the best option is to work at neutral pH. And in this case, the treatment times is measured in minutes. So not in hours, in minutes, okay? So these reactions are much faster. As for wastewater disinfection, we work in our group in the disinfection of real wastewater from secondary effluents in a raised pond reactor, and we compare the performance of the disinfection from in a tubular reactor, in a CPC, and in the raised pond reactor. We found that the disinfection process was similar in both kinds of reactors, and the treatment time was around 60 minutes for E. coli inactivation, total inactivation of E. coli, at least up to the legal limit in Spain. As for the removal of contaminants of emerging concern, we work with this kind of reactor too, a neutral pH, and we found that the solar photo-Fenton process was able to remove up to the 80% of micropollutants after 50 minutes of reaction, working with 5 different real effluents from different wastewater treatment plants in the Mediterranean coast in Spain. So Almeria is here, this is Girona, 1,000 kilometers away, one from the other. And to this end, we use very low concentration of reactants, ion and hydrogen peroxide. So, due to the very short treatment times, in our group, we were the first starting working in continuous process. That is, we changed from batch-wise operation, because when all the groups working, all the treatment with solar energy to treat wastewater used to work in batch mode, and we changed towards continuous flow operation. I will speak a little bit more to better show you how it's the continuous flow operation. And we did it for wastewater disinfection, as well as for micropollutant removal. Okay? So, as a case study, I will show you now, very briefly, how the continuous solar photo-Fenton works. In the picture, we have the experimental setup. That's just a real experimental setup with, in our research center, and a scheme of the treatment. So we have the wastewater effluent, the real wastewater. This is this tank, entering continuously to the reactor, and continuously the reactants, ion and hydrogen peroxide, are fed to the reactor. And we have a continuous outlet of treated effluent. Okay? So the water enters the reactor and gets out treated continuously. As microorganisms, we studied different microorganisms, the total coliform, E. coli, Enterococcus sp, and we worked in different seasons of the year, for instance, winter and summer, with a wide interval of irradiance. We always work with real secondary effluents, so treatments very close to the application, and we use two different hydraulic residence time, 60 and 30 minutes. And here you have the research for a case that was the operation at 30 minutes of hydraulic residence time. That is, the time spent by the wastewater in the reactor is 30 minutes. So in 30 minutes, we are able to disinfect the wastewater. And here we have the operation during 3 consecutive days. The first day, we started the reactor, the operation, in batch to reach total disinfection. And next, we started the operation in continuous flow mode. During the operation in continuous flow mode, the reactant concentration was 5 milligrams per liter of ion and 30 milligrams per liter of hydrogen peroxide. So very low concentration in comparison with other treatments of solar photo-Fenton. And we can see that this is the solar irradiance, the variation of solar irradiance along the day, okay? And morning, noon, evening, okay? The 3 days. And this is the bacteria concentration. The first day, we can disinfect the water, and in this period of continuous treatment, the water leaving from the reactor is totally disinfected. And we obtain a 33% of contaminant of emerging concern removal, additionally. As for the economic aspect of the treatment, we carried out an estimation to treat a flow rate of 400 cubic meters a day in a raised pond reactor. And the cost will change depending on the, I'm ending very fast. The final cost will depend or will be a function of the objective of the treatment. But the costs are very low, as you can see here, from 12 cents of euro to 50 cents of euro. And finally, after these results, in another LIFE project, the project Ulysses, we are going to construct a demonstration plant, a raised well pond reactor of 100 square meters, to disinfect wastewater in the wastewater treatment plant of the city of Almeria, because the wastewater treatment plant is very close to the university. So during this year, we are going to construct this reactor, and we expect to have very good results to show you in the next meeting. Thank you very much for listening.